Hello, everyone. I'm here with Marcel Moosbrugger. Welcome to the ACIT Science Podcast.
Hello, thanks for having me.
Just going to start off with a short introduction on you and your background. You are currently a computer science PhD student at University of Vienna, and your research focuses on understanding probabilistic programs and machine learning and stochastic systems and you're trying to understand all of them with formal methods. And where the term formal methods might sound very abstract and theoretical almost by definition, I'm sure there will also be a lot of interesting ideas to talk about the more formal theoretical stuff, but these formal methods are also becoming ever more relevant actually in practical applications. And your research is also connected to applications in the industry, for example, like a startup in the crypto sector or the security in the Amazon Web Services. So I find this intersection also super interesting, and I hope we will have a couple of things to talk about there as well, how these very theoretical fundamental work in computer science can also really find its way into the real world. But as always, before we get into the theories and the details and the material, I wanted to start off with a more personal question about what brought you into your field and kind of what your history is and how you ended up with your PhD in computer science.
Yeah, that's a very broad question. So to computer science, I knew that I wanted to study computer science like when I was 16. I was doing in Austria, it's called Handelsakademie. It's a high school which is focused on economics. So it is kind of atypical to then change and study computer science. But I would say more or less there was one teacher in our school who was only partly teaching, and for his main job he was a programmer. And he was just one day like asking the students, hey, who of you would be interested in programming? And then I was like, oh yeah, that sounds kind of interesting. I don't know what it is. And then he kind of introduced me to programming, and I really, I would say, took off with it. So I started reading about it and basically self-teaching myself about programming, and he constantly supported me. And then I knew, yes, that's something I want to do in the future. And then moved to Vienna, studied computer science here, loved it, stayed in Vienna for my master's, for a more theoretical master. And during my master, found my love to academia. And probably pretty funny is that at the beginning, before I was starting to study, I was constantly switching between computer science and mathematics. So these were the two I wanted to study. And I was like, one week I was, okay, I'm going to now start computer science. And then the next week I was, I'm going to do mathematics. In the end, it was computer science, but I think it's quite interesting that now, as you said, in the end, I ended up doing formal methods, which is kind of in the intersection between mathematics and computer science and uses things from both of the fields. So that
sounds like the perfect niche for someone interested both in mathematics and computer science. Was there in your initial phases of learning about programming any programming language you fell in love with, or how what would you think is a good way of getting kind of becoming interested in programming, or what a good transition into the field is? Because I guess a lot of people now need to start programming that don't particularly love it, aren't really drawn to it.
Yeah, so today there are so many resources. Like I remember when I was 16, it was like 10 years ago, there were already quite some resources, but now you have all these tutorials and Udemy and Coursera and whatnot. So that's definitely a good start to get a little bit of knowledge. You need just a little knowledge, and then you can already start building stuff. And that's what I would recommend. So I really had, when thinking back, like I knew nothing back then, but I just knew enough to get myself interested in it and start building stuff. And then you already see like, hey, I can build something basically just with my brain and my fingers and the computer, and I can basically make the computer do whatever I want. So whenever you're a user of a computer, you're always basically at the fate of the programs that you're using. Sometimes they crash, or if you want to do something in particular, you need a particular program. But when you know a programming language, you can do basically with a computer everything you want, and it's quite a powerful feeling. And also, yeah, the amazing feeling when you can just build something. You have an idea, and within a day, if it's a small idea, within a day you can build something and see your idea take form. And I think that's the best way to get into programming, to get like little projects and just learn by doing and continue learning the exact stuff you need for that project.
Yeah, there's a very direct feedback loop between what the code you write, and if you have like a direct application, you can basically test it, and then there's probably a bug, but then you pretty quickly get to a product, or like you harvest these small successes along the way, and that can be quite motivating.
Exactly. And yeah, but interesting, because at the beginning you said with academia and industry, I think also there is kind of this similar feedback loop, like between application and theoretical thinking. That's so at least my philosophy in my PhD is I really like to implement stuff and to see kind of my ideas running, so I can quickly judge if it works out or if it doesn't work out. And I think also there it's kind of a similar feeling. It's a similar feedback loop that you build something and then you discover, it's not working as I expected, and I'm missing some idea or some concept or something, and then you go back to your desk and pick out the pen and a paper and start scribbling mathematics, and then you go back to implementing. So it's a similar feedback loop.
Yeah, especially in the computer science, like, machine learning field, where you are so connected, and the pace is quite fast, that if you have an idea and if it just works well, it can be quite a simple idea, but then suddenly like thousands of people are adapting it and implementing it. I mean, you need to be lucky that something like that happens to you, but it can be quite, like, if you discover something that's relevant, it will get adapted very quickly, because a lot of people are on the lookout for these applications. I think that makes it quite interesting to be in a field that's like on the brink, or like on the boundary between industrial interests and also scientific interests, because it's not only about the knowledge, but also about the potential implications for the world. And
that's true. Yeah, especially, I mean, you are a physicist by training, right? I mean, you do now computer science as well, so. But if you compare it to physics, where you need a huge particle accelerator, which costs billions of dollars, and as a computer scientist, sometimes you need a quite powerful server or some computing power. But to sketch something out, you basically just need a laptop and can get going.
It's actually funny, because I was kind of asking for myself, because now I only recently got into programming properly, and really this kind of issue that you have in physics, that it's really hard to get to do experiments, is something completely different now in the machine learning environment, because you can really just sit in front of your computer and actually do experiments. But if you build an experiment in physics, you also need to construct an LHC or like huge ion traps or something. Then you need to get some vacuum pumps for 50,000 euros, but that's can be quite tedious in practice. But in machine learning, you just write the code, so basically the idea then falls down into the program, and then you can just test it right away.
Yeah, that's why I also like doing, I like doing research, because I like computer science. But particularly, I think doing research in computer science is very nice, because you can really contribute something, to the knowledge without being part of like a big group, like working kind of independent. I guess when you're a physicist, you really need to go to the LHC, or at least if you're an experimental physicist. But in computer science, you can kind of come up with your idea quite independently, and if it's good, it will be adopted.
Yeah. There's also this AI researcher, Francois Chalet. I don't know if you know him, but he's arguing.
From Keras.
Yeah, exactly. And he's arguing that you usually in scientific fields, you have this exponential increase in manpower that you need to get the same amount of knowledge increase. That's why in physics, because it's at the late stages of there's not too many low-hanging fruits that a single person can jump in and discover, but you really need to have these huge collaborations to chip away at the boundary of knowledge. And that's why you have 10,000 people at the LHC. But in computer science, in principle, it can just be one guy, like Goodfellow, for example, with his general adversarial network. He just went to a bar with his friends and thought, this could be an idea. And then he goes home, implements it in 2 hours, and then it's a huge, huge paper. I think this is kind of cool in computer science.
That's an interesting thought, yeah, and very true.
So maybe to go now a bit to the theory, you can start with your master thesis, because there you did some pretty theoretical work, I would say, but also with a focus on implementation. And your master thesis was also very successful, because you got the award for the best master thesis of the semester. So congrats to that.
Thanks.
And maybe we can go a little bit into what you did there. I don't know if this is a useful starting step, but we can also talk a bit about the halting problem, and maybe start out with the general topic of your thesis, but then go a bit to the basics from a computer science perspective and mathematical perspective.
Yeah, so on a high level in my master thesis, which then also turned out to be now continued in my PhD, so I basically switched directly from my master to my PhD. So in my master thesis, I looked at the termination of probabilistic programs. So you can think of just a normal computer program, and then you throw in some probability stuff. So you can also do some random decisions. You can either go left or right with some probability. And we all know that the programs, they either stop, they terminate, or they may potentially run forever. And in my master thesis, I looked at how to determine automatically with computer support whether or not such a program, which also contains probabilistic elements, stops or runs forever. And yeah, this is quite a famous problem without the probabilistic aspect. So if you just consider termination of standard computer programs, this was basically at the beginning of computer science itself, like Alan Turing, which is probably a name for most listeners, is considered the father of computer science. And he had this very famous paper where he showed that in general, deciding with another computer whether a program stops or not is impossible. So there is no program which can take another program and tell if the program stops, because it would be quite convenient. Like I was a programmer before in the industry, and when you program something and you would like to know, okay, is there an infinite loop in my program that I wrote? So it's crap. You would like to know that automatically, and Alan Turing showed this is impossible. And so it might sound like a contradiction that I worked on this, but what Alan Turing showed is that such a program, let's call it a termination checker, such a termination checker cannot exist if you consider the termination checker to be perfect. So if it always takes any program, and it always says yes, and it always says no, depending on the program terminates or not. So this cannot exist. But if you change either the requirement that it works for all programs, then it becomes, or there is work you can do. For example, you can just consider some programs of a particular form, which have some simplifications. Or you can also say, okay, my termination checker that I want to build, I allow that it has some false positives and some false negatives. So it kind of approximates the solutions or the answers to it. And then, again, there is something you can do. And that was kind of the story also during the last decades, you could say, because there are all these impossibility results in computer science, and especially in formal methods. Like formal methods has to do with computing or automatically telling whether some property holds for a program, like whether it terminates or whether it's correct, or things like this, things that you actually would like to know. And there are all these impossibility results. So it's not only the halting problem. Actually, there are, if you consider it theoretically, there are more problems which cannot be solved by a computer than that can be solved. It's quite interesting.
Yeah.
So if you're a mathematician, you know, like probably have heard that there are more real numbers than there are natural numbers. So the numbers 1, 2, 3, 4, 5, they are infinite, but they are still less than the real numbers, which contain pi and so on. And it's similar with the problems. You can also ask how many problems are there, and there are actually the same infinity as the real numbers, and the amount of solvable problems are just the infinity of the natural numbers. So actually there are just way less of them. But still, we focus on the problems, or it seems that most of the problems that are interesting for us humans are solvable, and for those for example, Alan Turing showed that it's impossible to solve them perfectly. We just don't solve them perfectly. We just relax it.
Yeah, there's this kind of interesting interplay between these impossibility results, which we can talk about the most famous one, which is probably Gödel's incompleteness theorem, that also relates nicely to the halting problem from Turing, and which has these almost metaphysical implications for the human rationality. It seems to be kind of insulted by that, or very disappointed, or the ambition of the Hilbert program was really strongly disappointed by this result. But then, in fact, to see how much implications that actually has for practical research is something different. And as you mentioned, the halting problem can be something big in practice, but then you just find your workarounds and you find your non-optimal solutions, and then it works out. If you look at it from a pragmatic perspective, it kind of works out again.
Yes.
So maybe can we start off with a relationship to the Gödel incompleteness, because we also talked a bit before about our common interest in this. And can you frame how this relates to Turing and the halting problem?
Yes. But let me first say that there is always kind of I hear it a lot, that there is kind of a negative flavor to this impossibility result of halting, or also to the incompleteness, which I will explain. But I actually think it's quite positive, or it's just the way it is. It's kind of like a natural law. It's like in physics, the uncertainty principle of Schrodinger. It's just how it is, and we need to work. We live in a universe where this seems to be true, and that's with which we have to work, and not say, okay, we live in a universe where this is impossible. And also it kind of ensures that I will never be jobless, so to say, because you can never solve these problems perfectly. And so there's always something you can improve, or the approximation you can improve. And so if you're sarcastic, you could say that if you don't want your job to be taken away by robots, you should work on something that's undecidable.
Yeah.
But yeah, the incompleteness result from Gödel. So Gödel was a logician, actually from Vienna. He was born in Vienna, or he was not born in Vienna, but he studied in Vienna. And when Gödel was a mathematician, there was this famous program from David Hilbert, who was a German mathematician, a genius. And Hilbert wanted to formalize mathematics, so to have a clear system of rules and clear system of facts which you assume to be true at the beginning. So you would, for example, assume like 0 is equal to 0, or 0 is the smallest number, and 1 is bigger than 0, like obvious facts. And then you have some fixed rules. And then he wanted, okay, with these rules, we can then prove everything we could prove theoretically about numbers. And he wanted, of course, that you also cannot prove something that's not true. So he wanted like this perfect system. And like he was really determined to reach this goal. He even said in a famous speech, he said this famous quote of him, which is also engraved on his gravestone, which says, wir müssen wissen, wir werden wissen. So in English, it's we must know, we will know. But then Gödel come along, like a very young, Gödel was at this time very young. And this young logician comes along, which hasn't done a lot in the field up until this point, and basically proves that this is not possible. That no matter what mathematical or formal system you have, like a system of proof rules and axioms, if it's strong enough, so if it can talk about numbers, then there will always be some things in this system which cannot be proven. And yeah, that was basically the end of this Hilbert program. Yeah, which shattered this. And it's very closely related to the undecidability or to the halting problem, which Alan Turing then studied. And the halting problem came afterwards. So Alan Turing proved that the halting problem cannot be solved by a computer program afterwards. But actually, the halting problem or the halting problem implies the incompleteness problem. For example, if you imagine that we had a mathematics like a theory which talks about computers, if you can formalize this, and this is not much harder than to formalize numbers, then in this mathematics of computers, the problem or the proof that some specific program terminates or not cannot be proven. If it could be proven, then the halting problem would be solved, right? So that's kind of the connection. They are very closely connected, and they both basically talk about some impossibility in something that we can know or not know, like either in mathematics or in computer science. And both of them, I would say, are also subject to a lot of philosophical thinking. So people love to take this further and then apply it also to areas which it shouldn't be applied, in my opinion. So to derive kind of metaphysical facts which prove that point, which is not always fair. It's a little bit like in physics, to compare it back to physics. Like a lot of people like to take quantum mechanics and the effects at the distance, for example, entanglement, to explain various kinds of phenomena they encounter in their lives, and it's similar with the incompleteness.
Yeah. I find it interesting because you mentioned the uncertainty principle and these kind of being things we have to deal with, but I would even argue that Gödel incompleteness and the halting problem, because they are purely mathematical proofs that need to hold for all formal systems, you could imagine them, every possible universe that you can imagine would deal with its own kind of version of Gödel incompleteness, because it counts for all formal systems. But you could imagine a universe where you don't have quantum physics, and you wouldn't have, as Newton imagined it doesn't seem to be like entirely necessary to construct the physical laws in a quantum physical way. But the Gödel incompleteness is an even more general the implication that maybe also connects to the way we think our human way of doing logic is the only way of doing logic.
Let me ask you one thing. How was it? Do you know how it was in physics when Schrodinger proved his uncertainty principle? Were the people also shocked, like that they can't know velocity and position at the same time?
I'm not sure. I think it actually came out of Heisenberg's formulation of quantum mechanics with this, there's a different way of representing it, because Schrodinger started off with the Schrodinger equation and the wave functions, and Heisenberg took this matrix formalism, and from that he derived the uncertainty relation. But I think they were shocked by all kinds of implication. I mean, Schrödinger's cat is the famous example of that Schrödinger constructed to show that quantum mechanics doesn't make any sense. Now took a life of its own, but he was deeply unsatisfied with some of the implications of this uncertainty around the state of the world, and that you can have this superposition of different states where the cat is both dead and alive at the same time. And yeah, I'm not sure about this, the implication of the uncertainty, but I think it must have had this metaphysical, like these philosophical implications, the same way that relativity also had this, seemed to have this philosophical implication of the time, where you have relativity in literature as well. That maybe takes it a bit too far, but you really have very similar shifts in, like, away from an objective narrative, where you in special relativity, for example, you have this idea that every observer is equally relevant, in a way that you can transform with this Lorentz transformation. You can transform from between different observers, and there's no inertial system that rests, and the rest is moving with respect to that inertial system, but every system is kind of has equal right to claim that it's the resting system. And this seems to be something that also developed in other areas, kind of shook the humanity's understanding of themselves, I guess.
If I remember, Einstein was kind of an opponent of quantum physics, and he didn't like these different effects. So I guess it was kind of a shock to some people. And then in the end, you could say that it was one of the best theories that human ever came up with, and it had amazing implications for technology and everything. And I would say also, kind of at computer science at the beginning, there were these impossibility results, or some negative things, and it turned out to be it gave rise to an amazing field of science and technology and all kind of new inventions. And it also wasn't that computer science was already there and people were trying to solve the halting problem. And then for decades, and then Turing came along. But for Gödel, it was kind of like this, but for computer science. So it was kind of right at the beginning of computer science.
Yeah, that's a very interesting perspective, that really showed it in the 30s, where you didn't have a single computer anyway, so it didn't seem to have any practical implications.
Yeah, that's true. That's true. And it's also an interesting perspective to work on something which was so abstract back then, but now it's kind of very, very relevant, also in practical terms.
Yeah, but it's crazy how the fathers of computer science, like Turing and von Neumann, already had a sense of the implications it would have.
Yes.
Really,
yes.
Also, this whole concept of the Turing machine is so powerful, because he realized that really everything is computation.
And also interesting, in my opinion, is that there are kind of different forms of or systems of computation that people came up with. So Turing came up with the Turing machine. There's also Alonzo Church, who came up with the lambda calculus, and there are much more. But all of these systems kind of seem to be equivalent, or not seem to be, they are equivalent. And so it seems like we kind of discovered what it means to compute something, what it means to be computable. So that's the Church-Turing thesis, that everything that is computable, that everything that you can compute is computable by a Turing machine or by a lambda calculus. And so this area, that's also why I then started switching to a very theoretical master's, where we studied all these things. It feels like doing natural science because it seems like laws of nature that you cannot compute some things, and what does it mean to compute some problem.
Yeah, maybe it would be cool to delve deeper actually, a little bit. So how would you define computation? Or do you have any like nice intuitive definition of what it actually means to compute something? Or maybe we can also talk a bit about Turing machines.
Yeah, so I mean, I heard all about Turing machines and lambda calculus, and I know that they are equivalent and there's nothing better than them. So I would just give the definition of a Turing machine.
Yeah.
But to break it down in easy terms, I would say you need just a finite set of instructions. That's what computation is. You have some clear rules, you have an input. So you want to compute a function like, let's say, x times y, and you have an input, which is x and y. And then you have a clear set of instructions which are unambiguous, which you can follow, and in the end you get the result that you wanted to compute. Actually, computation it's very, very intuitive for all of us. So what an algorithm is, it's very intuitive. In primary school, we all learn how to multiply numbers, and with this, I cannot do it anymore because now there are calculators everywhere. But we used to write it line by line and then add the numbers up, and that's kind of an algorithm to compute something. It has a very clear set of instructions with an input and an output. Yeah, and Turing machines just take this intuitive idea to another level, like formalize it really in mathematical terms. But in the end, it's also just that it's a set of instructions, and
probably the idea from a computer science perspective that's important is that you can take every input and encode it. You have this dictionary, or every sequence of possible inputs can be encoded and in the alphabet that's used on the tape, and then you can basically, in computer science, everything on computers is done by ones and zeros, and you can always find a mapping that encodes it with ones and zeros. So that also takes the highest level of abstraction in this regard.
Yes, yeah, you can always, that's also an important fact, because if you have a set of instructions, not all set of instructions are equally powerful. So with a multiplication algorithm and the things you learn in primary school, you cannot compute everything. But then, what these logicians also studied is kind of what set of instructions are more powerful than others. And Alonzo Church came up with his set of instructions and his system, which was lambda calculus. Turing came up with his own, it was the Turing machine and this set of instructions. And that then turned out to be equivalent to each other, and nothing more powerful was invented since then or came up. Now, no one came up with a more powerful mode of computation. Even quantum computers, they cannot do more than Turing machines. And so, that seems to be the ultimate thing what computation actually means, or formalized in that in that way. Now I wanted to say something, but I forgot. I will come back.
What I was actually wondering right now that you mentioned it, like how does probability then, because you also talked about these probabilistic components of these programs, how does it factor in if you have a program that incorporates some kind of like non-deterministic components, but that still count as a Turing machine?
Yeah, you need an external source for probability. Yeah. I'm not so familiar with the theoretical models of computation with probability. But a Turing machine definitely cannot produce real probabilistic numbers. It can produce pseudo-random numbers. You can implement a pseudo-random number generator on a Turing machine. But even if you give it a kind of an oracle which produces random numbers, this new Turing machine with the additional random number generator cannot compute more functions than the original Turing machine. Yeah.
It reminds me a bit far-fetched, this association, but with this whole idea of either the whole universe is deterministic, then I mean, in principle, if you have randomness from one source, you could also model this different source of randomness as a Turing machine, because it's also deterministic and kind of also only running its code. But the only way of getting true randomness in our perspective of the universe is to move to quantum physics, basically make a quantum measurement. But then you actually have true randomness, but this true randomness doesn't get you anywhere because it's just completely random and you can't do any computation with it. So in the same sense, in free will, because sometimes people pretend like you need you need quantum physics to get out of the deterministic universe, and then you can actually do free will decisions, but that would just mean you need to sample something randomly quantum physically, but then there's like no component of yeah no useful information in that random signal, so it also doesn't help you to make any free will decisions. That made sense.
So what is your take on that?
On what?
On free will. I obviously have no idea about physics and or just limited idea. But yeah, this discussion that in a deterministic universe there is no free will and or kind of cannot be free will, this argument, and that you need quantum mechanics. But now you said basically that it doesn't help you either.
Yeah,
But so
I feel
what
like
is your take?
to my mind, there's two components to free will. There's this, we can call it ontological component. So is there something like free will that actually exists in the world? And from that perspective, if I'm a physicist enough to have been taught that you have an initial state and then you have the time evolution of a system, and the initial state completely determines the time evolution of the system. So in principle, if you have a complete description of the current state of the world, then you also know what's going to happen in the future. In quantum physics, that's not completely true, because then you only have the evolution of the wave function, which has some probabilistic element to it. But there's for me no way, as I just also was talking about, no way of getting free will into this anywhere, because then it's just really pure stochasticity and pure randomness that doesn't correspond to anything that we mean by free will. But then you have the other perspective on free will, which is this more epistemological, because we are brains in the world with incomplete information about the state of the world. So for us, we only have partial observation of the state of the world, and that means if we in our brain simulate the time evolution of the world forward, so if we look into the future by thinking what's going to happen tomorrow, how's the weather going to look like tomorrow, we do these predictions based on incomplete information, and then we basically have a set of potential trajectories in front of us, and then we make a decision. So our self model of the world selects one of these possible actions that it can do based on these predictions about what the world is going to be, and this is what we perceive as free will, I would say.
But
Because
isn't that decision you make, because your brain is basically part of the global state description, and isn't then that decision just an illusion?
yeah, definitely. And I think
Okay,
this,
so you think free will is an illusion? That's
yeah, I think,
your
I mean, it appears to us as if we have free will because we have incomplete knowledge of the world. So it's kind of a mental construct that allows us to select between different action sequences that our brain and body can implement, because our brain has also a probabilistic model of the world, and it needs to, yeah, find best actions based on this probabilistic model of the world. And but in principle, the brain is also a deterministic system. But I think this perceiving ourselves as having free will is something useful from this perspective, because we can actually, like, our brain is actually kind of selecting between different sequences in the same way if we program a robot now, that it can also select different sequences based on input, and the robot is also embedded in a deterministic system and is itself a deterministic system. But if you move to that lower layer of abstraction, then I think it makes a lot of sense.
yeah. As you said, it makes sense to think, even if we didn't have free will, or if we have one, to think about just having one, because we feel like we're having one.
Yeah.
Yeah, I know all these theories about free will. or at least heard about them.
Yeah.
But in my daily life, I try not to think about it.
Yeah.
Because I just get headaches.
Yeah. There's also with consciousness, for example, this interesting perspective because it's funny that human beings are so concerned with thinking about free will and consciousness, kind of this meta problem. Why do we think it's such a big problem even? So
True,
well,
yeah.
and there seems to be some kind of social function because we really, especially in our Western culture, free will and consciousness are so entangled with our moral values. We think consciousness is really the bottom of our moral judgment. We say if something has consciousness, it has moral implications. If it doesn't have consciousness, we can just destroy it or kill it. It doesn't matter. And for free will, if someone committed a crime based on their own free will, then it's a crime. But if it was an accident, it's not the same. So it's so tangled up with our perception of ourselves.
Now we drifted off.
Yeah, we definitely drifted off without any free will of our own.
True, yeah.
That's at least reassuring. So maybe we can go back to your master thesis and some maybe some practical implications. You wrote this program and published this code. So how does it actually become relevant in practice for debugging, for example? Or what can you do with it?
Yeah. So exactly. I remember we were at my master thesis, and then we went to halting problem, incompleteness, and then we took off. Yeah. So in my master thesis, to say it again, I basically considered the halting problem for probabilistic, like with a probabilistic element, and for some restricted programs. So that was one restriction. I don't consider all programs, but just some restricted formal programs. And although I did not solve it perfectly, so instead of always saying yes or no, there's also the possibility that the tool I developed just says, I don't know. So either it says yes, no, or I don't know. And it was more of a theoretical work. So how could you automate it? And then I had a prototype, which I programmed and to basically test the ideas. But I would say it's still kind of an academic prototype to benchmark the ideas we had and to evaluate them scientifically. But in general, this master thesis that I wrote falls into the category of formal methods and program verification. I would say, so you have a program, be it probabilistic or not, some program, and you want to verify some property. Like I said before, like termination is only one property, but you could also have that it cannot be hacked in some specific way, so that there is no vulnerability. Or for example, if you have concurrent programs, so two programs who run concurrently, that there is no race condition, because that also leads to errors. It would also be a property. And for that, in practice, there are quite some tools, which are, I would say, especially in the last few years, a few tools came up, which people are using, especially in microprocessor development. It was already a big thing, formal verification. So verify that your microprocessor is doing the right thing. And also in some areas where the stakes are very high. So for example, in NASA used quite some formal methods. They even have a formal methods team. Not sure what they actually verify, but you could imagine that at NASA, it's quite important to know that at least some part of the program is exactly doing what it should be, because there are human lives at stake and billions of dollars. So it makes sense to have a whole group of humans and pay them to verify that such a problem does not exist in the program. Yeah, and that's also the very important distinction between program testing and program verification. So a lot of people have probably already heard, or at least if you have programmed, about program tests, which you should write when you write a program. So where you basically run the program on specific inputs and you see if what you get is what you expected. But program verification is much, much more than that. It really is about mathematically proving and automatically proving that no bug exists, or that some property just holds and you get a proof for it.
Yeah, you sent me this article, which had this nice quote, "Why testing is not enough for $1 million code," which is trying to illustrate this example of.
Yeah. And in the last, especially, I sent you also a link about a company which tries to verify smart contracts. So smart contracts, for those who don't know, is basically a piece of code that runs on a blockchain of some cryptocurrencies. For example, on Ethereum, you can have smart contracts which automatically send out money or receive money, store money, and so on. And there were quite a few hacks for Ethereum smart contracts. For example, the DAO hack was very famous, where millions of dollars were stolen. And especially in these areas, I think cryptocurrencies and smart contracts are quite a blessing for the research area of formal methods and verification, because I think, in my opinion, it's the perfect domain to use these ideas on, because there's just a lot at stake, a lot of money is involved, and you really don't want to have any possibility that this money gets lost, or there is a possible vulnerability. And also, smart contracts are some very specific programs, to come back at this, because verification is also impossible in the ideal case. So you cannot have the perfect verifier which takes a program and some property and then tells you yes or no. But again, smart contracts are not all programs. They're very specific and also quite small. So usually a smart contract has about a few hundred lines of code maximum.
So maybe how can you, what I find always a bit abstract or hard to understand is how you actually get from the program to a mathematical formal framework in which you can prove that the program is correct, or you can basically prove that it's bug free. How does this translation process actually work?
That's a very good question. So you can translate a program on different levels, but you can, for example, for smart contracts, you can compile them first and then work on this level, or you can directly work on the program basically you wrote, or the programmer wrote. And usually it works compositionally, so instruction by instruction. So you would, of course, it depends what logic you choose. So the big picture is you take your program and you convert it in some logic. And then we use all the knowledge and all the research that has been done on logic to solve the problem. And you want to choose a suitable logic first. So you want a logic where you have arithmetic, you can do plus and multiplication, and you have arrays in the logic already. So then the translation comes pretty straightforward. You can just translate, for example, an assignment. If you have an assignment, you have a variable x and you assign it to y plus 1. Then you would also have a variable in the logic named x and a variable named y in the logic. And yeah, just basically that translation would be quite immediate. For what's a little bit different, for example, to give you an example for that, if you have an if statement, if you know about that, you have an if statement. So if some condition holds in the program, then you do something, and if it doesn't hold, you do something different. Then you would use something called an implication in the logic. You would say the if condition would become basically the condition for the implication, the first part, and then you move to the you then put there after, or on the right side of the implication, you put the code that corresponds to the case where the condition is true and so on. Yeah. But some approach is also to use the compiled code, to first compile the code and then verify that the compiled code satisfies some property that, for example, cannot be hacked. And some advantage for that is that there are just less instructions. So usually when you compile some software, it compiles it down to some other language, if not to machine code. It compiles it down to some language where there are just a very limited set of instructions. And that's the advantage then, that you can just to deal with these few instructions and can verify then the code which also holds for the program which you wrote.
Yeah, there were a couple of interesting points in there that maybe we can track back on a little bit. So maybe first to clarify what a logic actually is. What do you mean by that?
That's a very valid point. Yes. So a logic is a mathematical framework which formalizes, I would say, a little bit how to get to conclusions given some assumptions. Like basically how we humans do it as well. Like we have some assumptions and then we do some reasoning and then we arrive at some conclusion. And that's exactly also what we want to do in verification. We have some assumptions. We have, for example, a program, which is how it is, and this is our assumption, this is our program, this is how it is. And a property, for example, this is not hackable, this is our should not be hackable. And then these are our assumptions, and we do want to do some reasoning and then arrive at the conclusion, this is true, this is really not hackable, or also maybe it is false. And the logic is basically just a mathematical framework which can deal with these things. You can encode something in the logic, and then in the logic you can do these kind of deductions and arrive at some consequences. And then there are different kinds of logics. So, for example, the most simple logic is called propositional logic, which is only to do with ones and zeros. So, for example, you can express things like if it rains, then the street is wet. So you would have a sentence like if it rains, which is either true or false. So it rains is either true or false, and the street is wet can also be true or false. And then you can express something like if it rains, then the street is wet. It must be a very simple logic, propositional logic. And then you can combine different sentences or different propositions and assumptions, and then arrive at some conclusions. Then there are more complex logics, which already in the logic you can do plus and minus and times. You can do some arithmetic, and then you can basically go up and up and up and add more things to the logic. But then in the end, you again run into the problem of undecidability. That at one point the logic is just so powerful, or incompleteness, right? I said at the beginning, if you have a formal system which can talk about arithmetic, there are things that are true you cannot prove. So, for example, the most simple logic, you can always get an answer from it, but you cannot express very much in it. And if you add more things, it becomes more useful, but also more dangerous in terms that you may run into impossibilities. And so it becomes also a game of choosing the right logic. But there are tools out there which literally you can download, and you can encode something and ask the tool, is this true or is it false? And these things, for example, there's this SNT solver, which is kind of a logic solver from Microsoft. It's called Z3. And this is a lot of times at the heart of these verification programs. So you would encode the program into the solver, into the logic solver, and the property, and then ask it, is this true or is it not true?
I also find this hierarchy of how computers work quite interesting. So maybe we can also go into that a little bit, because you start out with your program maybe on the highest level in Python or something, and then that gets automatically translated down the pipe until it ends up in machine code and then gets run on your CPU, for example. And you always need to take this translation process kind of into account, and then I don't know how you can compare that, but maybe a programming language also constitutes some kind of logic, because it also incorporates operations. How do these two relate?
So I would say you do not have to take it into account, the translation to lower level, or at least you shouldn't take it into account in the ideal case, because that's kind of the beauty of abstraction. In computer science, everything is about abstraction. So first you have the hardware, where literally the processor is there. It only works with zeros and ones, and it shifts around and bits and allocates memory and so on. And then you have some abstractions, and suddenly you are at Python, for example, where you don't have to worry about memory, about the processor. You can just express your idea in Python, or your program in Python, and run it. And that's kind of then the beauty, that you don't have to think about the process. You basically can program in Python without knowing anything about CPUs or in random access memory. So the connection between logic and a program. So I would say there is quite a distinction between them. So for example, a program literally produces something. You give it an input, you run it, and it produces something. Whereas a logic is something you want to encode truth in, or you want to reason about something external. Yes, so a logic, for example, there is no notion of execution time or something, or no notion of this happens first and after this instruction happens, whereas a program runs line by line and you get the result. And the logic is just a way to express some truth, something that should be true or should not be true. That's what I would say.
I was wondering about not sure I'm getting the point right by Hofstetter and Gödel-Escherbach, but he's also talking about these formal logical systems that then only acquire meaning if they are mapped onto some kind of structure in reality. So we can define this formal logic, which is self-contained and true by itself, but if we say, oh, this abstract logical structure now corresponds to this computer program, then it suddenly acquires meaning to something external, and then the logical operations can correspond to something that actually has runtime, or the inputs can find their way in or something.
Yeah, that's true. You can, if you study logic like I did in my master's, you can construct your own logic, so to speak, and your own logical system, and you construct it basically again by having some rules and how to combine things. And yeah, then the question is, how useful is it? And you can construct very abstract kind of systems which don't really correspond to anything, like you said. But yeah, in the end, when we want to do something useful, we always want to model something. We would like to our logic that we construct to correspond to something in reality. Like, for example, that you can express something that's meaningful and then deduce from that something that you also consider meaningful. For example, like with the street is wet and it rains example, that you really can encode your reality in the logic. And similarly, when we want to reason about programs, so we write a computer program and we want to automatically reason about computer programs, you would construct a logic with that in mind, so which kind of corresponds to what you write down in the computer program. And so in in this logic solver, which I mentioned from set 3, for example, in the logic, there is a concept of an array, which is a program construct in the end. But they put it into the logic, and there is a whole logic of arrays that, for example, when you add something to the array and then you remove the first element, then this is the element you added, for example, which is very trivial. Like you would say, okay, this is obvious, but that's also the thing of logic systems of your logic. You have to really define everything, and then you can. That might be tedious, but what you gain is that you automatically, a lot of times, can then deduce consequences.
Yeah. Also in mathematics, it's like tedious to define. And sometimes it's probably not obvious how to reason, but if you have a proof that's self-contained, then I mean, it's just there. Everything, there's no holes. It just follows perfectly from itself. So you can even think about, like, is it the power of the person reasoning or the power of the formal system? If the formal system is powerful enough, then in principle it's working itself out, so to speak.
Yes, if you can, if there are not too much possibilities.
Yeah, I mean, in practice, it's always something very different.
Yes, true.
I wouldn't say that mathematical research is very trivial at all.
Yeah, but that's why we have also a computer. When you have a huge formal system, and you need to try 1,000 different possibilities at each step, then for a human being, it might be very difficult. Also, if you try to reason about a huge program with 1,000, at least, which is not huge, but already 1,000 lines of code, like as a human, you cannot keep track of everything, and you will make an error for sure at some point. That's also why it's then very useful to use computers to reason about programs, because you can let them do a lot of instructions.
Yeah, it sounds very meta that now we are teaching our computers to reason about themselves, so to speak. I think that's also in the AI community. I think we're slowly taking ourselves and our limited brains out of the loop because our computers are becoming too powerful.
Yeah, it is kind of a self-reference, and maybe that's also why some paradoxes are popping up, right? Because I think we didn't mention it, but at the heart of the incompleteness theorem of Gödel is a self-reference, so a mathematical sentence which talks about itself. But I think it's not that far-fetched to use computers to reason about programs, because if you do programming and you have a nice programming editor where you program, the editor will give you some hints. Like it will say, oh, you didn't, you forgot a bracket here or something. And it also does some form of reasoning. For example, if you have a type system like in Java or in C++, the editor will automatically tell you if you use the wrong type, which is already some form of formal reasoning. So it automatically uses, oh, the type you should use here is not the type you put in. And the thing we do in our research or also formal methods in general with these logic systems and logic solvers and verification is just taking that on another level. So not only about types, but maybe for smart contracts about hackability. But that would be the idea. The editor tells you, hey, you did something here, and that's why this attack is possible. So you change it.
Yeah, we can at this point also connect this a bit to your current research. You mentioned your group is also collaborating with Amazon Web Services, and there are some very direct implications when it comes to hackability and security in the cloud, for example.
So we in our group here in Vienna, so my supervisor is Laura Kovac, if I didn't mention that. Our general goal is to, in the whole group, is to reason about programs and to prove properties about programs, be it security or functionality. And within that, some of the students I was not at Amazon, but some of the students, some of my colleagues were there for an internship, and or not particularly at Amazon, but at Amazon Web Service. So the part of Amazon which provides cloud computing, and they use formal methods quite extensively at Amazon Web Service. They even have like a big group, how's it called? Amazon, something like the Amazon Automatic Reasoning Group or something like that, where the whole purpose of the group is to automatically, again, tell whether or not some properties in the cloud hold. So if you rent some servers on Amazon Web Service and you set it up, you can activate something on Amazon Web Service, which then tells you whether or not your server is reachable from the outside or not. So if there is some confidential information, if you have some secrets or some very important data on that server, you wouldn't want it to be accessible from the outside, and that's what they, for example, check automatically. But the cooperations we do here at Vienna with the other groups are always, I would say, quite academic. So we do academic research with them. But for example, the head of the Amazon Automatic Reasoning Group, I'm not sure if that's the real name, I just call it that way. So he was, for example, also, he was at Microsoft before, if I remember correctly, but in the research department of Microsoft and doing academic research there, and then changed to Amazon doing these things. Another cooperation, for example, also we have is with this, or a few colleagues of mine did an internship for smart contract verification, which we talked about. And also that is a spin-off. It's a startup from Israel, which was a spin-off from the university there in Haifa. And also basically the CEO of the company is also a professor, and we work together with them on an academic level.
Yeah, it's quite fascinating in this whole field, also in machine learning, obviously, how closely intertwined industry and university research are with these big tech companies. Yeah. Also funding a lot of the research.
Yeah, especially the big tech companies. Most of them have their own research department. I hear a lot about Microsoft, so we are also working together a lot with the automatic reasoning group at Microsoft. So they also have something like that. They even developed Z3, which I talked about. They have basically very, very big research departments, which just do academic research, and of course sometimes it's very useful for them as well.
Yeah.
So I think that's also the goal of the companies.
Yeah, I think they are doing sufficiently well financially with these web services that they can afford to get a couple of. Yeah, also in the machine learning field, I read this frequently that Google, for example, just puts a lot of money into research, and it's all open sites. It's all completely open access. They don't protect anything anymore. They just publish it at NeurIPS and ICLR, ICML. Like, I feel like a third of the paper I'm reading in my everyday life are from either Google or Facebook or something.
Yeah,
it's quite interesting.
Yeah, I think also it's very important for them to have it open access. So first of all, I'm a researcher, and I want the research to be open access, and I think that's the right thing to do. Yeah, but I think also you get much better research to work for you if you allow them to publish open access. Because if you really want to hire a researcher which is passionate about it and passionate about research, they would be very reluctant if you tell them you cannot publish this. You have to keep it for the company.
Yeah, it seems to work for both sides in a way.
Yeah.
To make it less protective. That's also a good signal for science that really the most open you can be is also the most beneficial for everyone in the long run, hopefully.
Mm-hmm. when I was doing an internship in America, there was a big dinner, and a manager who was managing a team in Microsoft, or was it at least a big company, the research group at a big company. And he was telling, basically, we are hiring the brightest minds and just let them do whatever they want.
Yeah, it's going back to the Bell Labs ideas in the I know at IBM in the 60s, 70s. So many stories you hear. It's just they give someone money for 10 years and leave them alone in the basement. Then something awesome pops up.
Yeah, for sure. But to go back to formal methods, I think you can see that it is quite important, and or gains more and more importance, these formal methods and verification, because all the big companies, they have their own formal methods team and try to use formal methods to either secure their cloud or secure their smart contracts. And I think it's quite an important topic and very relevant, especially in the last 10 years. When the whole, or last 20 years, when the computer architectures grew and grew, cloud computing came up. And probably in the 20th century, it was more an academic effort where all the foundations were developed, the logics, how just everything, how to reason about programs. And then, but in the last 20 years, you can see now that the big companies are trying to develop their solvers, or startups are popping up, spin-offs from universities. So I know at least 5 startups now who are doing some kind of reasoning about programs.
Yeah, it's so interesting, because that's really not something you hear a lot about yet, like in everyday life, or maybe in the media or something. It's still a bit under the radar, I would say.
Yeah,
it's becoming so relevant.
Exactly. That's why I was very happy that you invited me on the podcast. Because yes, for example, for machine learning, which is another big thing which came up in the last 20 years, it is very awesome, undoubtedly, but it is also very popular. So everyone knows about it. Like even when I'm out at the bar, not now in Corona situations, but before that, when I was out in a bar, like people or friends of mine who did not even know computer science, they were, what about artificial intelligence and machine learning? They all know about it, but I think it's equally important. Like it's at the same level, these formal methods and verification. It has a huge history which goes back basically to Gödel and Turing. It has a nice storyline, you could say. It has drama in it at the beginning. It has ups and downs. It's very powerful. You can do really amazing stuff in it, but nobody knows about it. At least outside of the people who work with it.
Remind me of something we also, I think, talked about a little bit, but this whole idea of explainable AI and some of the inherent issues with uncertainty you have in the classical machine learning neural network architectures, where you really have different kinds of uncertainties, and you really need to think about how much you can actually trust your predictions. You also wrote an article about this, so I thought we can maybe also chat about this a little bit.
Yeah, true. Yeah, that would be then when these two phenomena meet, machine learning and formal methods, when you try to, given a neural network, say something automatically about it. So, for example, you have probably heard about adversarial examples where you train a network and you train it to detect animals, let's say, and now you give it a picture which is clearly a cat, and the network detects this is a cat. But then you change just some pixels, like you change it to black, and for a human it's still very obvious that this is a cat. But now the network is convinced that it is a pigeon. it's 100% convinced this is a pigeon. And then the question is, okay, what is this network actually learning? What is important for the network? What has it learned? Has it really learned the concept of a cat? And what does it mean to learn something for the network? Yeah, and then you can start asking a lot of questions which you would also like to automatically answer. For example, that you cannot, that would be a nice property to have, you cannot change a few pixels and radically change the output of the network, which is, for example, very, very important for self-driving cars. Like, self-driving cars drive around, and they also use machine learning and neural networks to see basically what's around them. And if they see a stop sign, and there happened to be a little bit dirt on the stop sign, which basically mimic these black dots, and suddenly it mistakes it for a, you can go 80 kilometers per hour sign, that would be a fatal mistake. And yes, and there is also it's quite a hot research area right now, explainable AI and verification of neural networks, where you try to tell why is the network making the decision it made, or defend against these adversarial examples.
Yeah, I heard during lunch we talked about a similar example of this big study in England, I think, being published about they being able to predict if someone was infected with corona based on a scan of the lung or something. It was like a nice big publication, but they didn't really manage to figure out where the network actually classified the pictures so well. And then they, like after publishing, found out that I think the edge of the picture for the COVID patients was looking slightly different. And so the image classifier simply picked up on the edge and ignored all the rest. And
yeah, that is an amazing example. Yes.
So it would have been very useful if we can just ask the network, and then it's just saying like all the information is coming from the edge.
Yeah. There is actually there are some approaches already. I'm not sure how far they are in terms of practical applications, but I've seen a lot of papers work on that too. At least in the image processing case, where they try to say what's on the image, that you can kind of highlight what is the most important part for the neural network. Yeah, so I've seen it. But the article I wrote about it was about uncertainty, which is also kind of, you would like to know how uncertain is the network. Because the neural network will always give you an answer. There is no unknown. You give it an image. If you train, for example, to go back to this example, the network on animal images, and if you give it a car, it will give you an answer. Like the animal it believes is most similar to this car, or you don't know, it gives you just something, and then you would like to know, like, how certain is my neural network with the prediction. And there are quite some things that have been done in the last few years, but yeah, before that there wasn't much there. Like the neural network gave you some answer, and take it or leave it, you
Yeah,
you work with it. Yes.
Yeah, that's like a person in real life that would come across as pretty like arrogant, or like if a person just said, "Yeah, I know everything," like just ask me something, and this is a cat, this is a dog, I don't care. Yeah.
Yes. Yeah, but it is kind of our fault. Like humanizing these technologies is probably not such a good idea, because we didn't give it the chance even.
Yeah. No, but I just been relating it to. Yeah, I think that just illustrates the issue that a central part of our reasoning is not only making statements about what we know, but also having an estimate of the uncertainty inherent in the world. I think this is really crucial in our own reasoning, and so these Bayesian perspectives on neural networks, for example, are so important, because then the model itself becomes, you can make probabilistic statements about the model itself, and you don't only learn one model and you say this is the perfect model and it can predict everything, but you say, yeah, based on the data, I have this set of models, and they also form like a probability distribution, and then inherently it could be that that a lot of different models describe the data equally well. So I can't really put too much belief in my estimate. I think this will be super important, especially in medical contexts or self-driving cars that you mentioned.
Yeah, very much. So I mean, these neural networks are now everywhere. We use them everywhere, and also in situations where there's a lot of at stake in self-driving cars where potential accidents can happen, and especially in the medical area for diagnosis, they're everywhere. And it's as a computer scientist, I think it's amazing that it hasn't been done already. That this wasn't done right at the beginning when it was used for medical diagnosis, because it's obvious that you want to know how certain is this black box that I don't know what it's actually doing. How certain is it about this diagnosis? Yeah.
Especially if you take humans out of the loop, or if humans lose the ability to even judge how good the estimate of the network is, because then we have no way of checking it. But that's probably also a good point where formal methods come in again, because they can then take over these sanity checks in a way.
Yes. Yeah. So both probability theory and formal methods, will play a factor, I think. So like the things that you said, like Bayesian neural networks, they're mostly based on probability theory, because where you want to know uncertainties, how uncertain is it, and formal methods also with logic, where you do logical reasoning about these networks. And that's also why I'm so passionate about the things I'm doing now in my PhD, because it basically is formal methods mixed with probabilities. Although I didn't do anything with neural networks up until this point, I think for being useful in everyday situation, and also in situations where there is a lot at stake, probabilities and formal methods will be, and an interplay between them will be very important, play a crucial role.
Yeah. To move on to some meta questions, maybe already like staying with the probability theory, it's actually like thinking about formal methods and probability theory. Would you say that has kind of shaped also how you live your daily life, or do you catch yourself thinking differently about things?
Yeah, definitely shaped my life, because I'm working with it and I'm breaking my head about. But if I mean, logic definitely made me quite annoying sometimes, because I'm saying this is actually not true what you say from a logical perspective. Because, for example, you have this thing that from something that's wrong, everything follows.
Yeah.
So, for example, the sentence, if the sky is green, then I'm a cow, is true. And so such things. And there is this one game I like to play with my family, which it's a board game, and you have to have some kind of basic judgment about probabilities, and I'm constantly winning the game because I have a good feeling for probabilities.
But do you compute them, or do you try to find like formal expressions for the like the probabilistic structure of the game, or would you say it's more of an intuition?
No, I try actually to calculate it, but not exactly. So you have to. It's the game is called Bluff. So you have to kind of keep track of how many dices are still around and what is very likely to. So how many points there are in total, and you don't see all the dice, so you have incomplete information. And I try to kind of judge in my head like what's roughly the probability of something.
Yeah, nice. like the definition of you must be fun at parties, like being very logical and crushing everyone in your board games because you just computer.
No, then there are other board games where I lose all the time. Yeah, but I also try to kind of know when to use the logical reasoning and when not. So at the beginning, when you learn first about logical formalisms and that you can reason with them, you like to apply them everywhere. But soon you notice when you learn about non-classical logics that humans are far from logical or logical beings in a mathematical sense, and so it's not rational to apply that.
Yeah. I think the more time you spend with it, it becomes just you move out of that tendency to view everything through that lens again. We had that joke in our first semester because one of my colleagues like back in the first semester, then he had this very poignant image of him like standing after our exam period, standing in the nightclub with a glass of drink in his hand, and then constantly while he was dancing, thinking about the like potential energy contained in the gravitational field of his drink or something like that. Like this inability to get distance yourself from this way of thinking about the world. But I feel like also move out of it again, luckily.
But I think it also provides a very great perspective. If you don't annoy everyone in your surrounding all the time with it, it provides a beauty because you for example, I think don't think that if you understand a physical concept that it becomes less beautiful to observe, so to speak, and you appreciate it actually even more. Or if my computer does something, or sometimes I'm just fascinated how that I can, for example, here have this podcast with you in another country over satellite communication. And
I think beautiful. This is actually a very nice point. There's also this Feynman video, this Ode to a Flower, where he's talking about like taking a look at a flower and science only adding to the beauty of it and the complexity and richness of the world. And I feel like, especially in our day and age where computer science and logic and formal stuff is usually portrayed as kind of cold and hyper rational and nerdy, I feel like everything related to computers is like the most magical thing of our time right now. Like everything happening around us is just completely crazy that it works. And if you teleport someone like from 200 years ago, or even if you teleported Turing to 2020 and showed him what actually happened with computers, he would still be completely blown away. I feel like we lose track of that magic sometimes.
Yes, we are much too used to it. Yes, it's amazing, I think. So, of course, there are risks to it, and we need to make sure that we use technology in the right way. But all in all, there are so many amazing possibilities that are enabled through this.
Yeah, and especially if you go from like the concept of Turing Machine and know that he made that up like in his mind, and then we pushed it forward and implemented it in technology, and 80 years later we have this. It's pretty mind-boggling.
True, and in some sense it's also a collaboration between our two fields, between quantum physics and computer science, because you provided the circuits and everything, and it's also a good illustration of interdisciplinary collaboration.
Yeah. Do you have any favorite books, like maybe also within the field or outside the field, that really shaped the way you think?
I think you mentioned it, Gödel Bach.
Yeah.
Yeah, it's quite a hard read, to warn everyone who wants to read it, but just to read a few pages every once in a while, it's an amazing book. There's what I can really recommend is Logic Comics. It's Logic Comics, like with one C. It's written by a very famous computer scientist from the 20th century who worked in complexity theory, and together with some very talented illustrators. And it's basically a book, which is a piece of art itself. It's like a comic book, but it presents the story of this crisis in mathematics, of the paradoxes who came along, and then David Hilbert trying to solve them, and Gödel basically crushing it with his incompleteness theorems. And that I can very much recommend. It's very nice to see it, and also a very nice read.
Nice.
Have you heard about it?
No, I actually haven't heard about it.
I can really recommend it. It's so cheap. You can buy it on Amazon, and it's a piece of art just to have it.
Yeah, awesome. I'm really happy I started asking this question because yeah, there's always very interesting input that not a lot of people have heard about. Maybe as a final questions, are there any takeaway messages, takeaway experiences or insights from your, now that you moved into research and are doing research professionally, that you've gained, if you could think of yourself maybe 2-3 years ago, how that transition was shaped and how to go about it?
The biggest thing I had to learn is to accept setbacks, I would say. So I worked in industry before, so during my bachelor's, and in industry, most of the things you have to do is very clear. So there are solutions for it, and there are some tasks you have to do, and you do them. Not that it's uninteresting, but there is creativity involved as well, but you can do it and you can plan it very well. Whereas in academia or in research, sometimes you're just tackling problems where the problem itself is maybe even unsolvable, or nobody has ever thought about it. You need to go back and change the question itself. And it's this process of trying something, failing, and going back to the drawing board. And at the beginning, I would say I was much too what's the English word? Ungeduldig, impatient.
Yeah.
I was much too impatient and wanted to do it in the same way as in industry, and that I had to learn and also enjoy it. That's very important. Enjoy the process.
Yeah, I think that's enjoying the process is really important, but it's sometimes very difficult, especially in paper deadlines or
that's true. Yeah.
Debugging periods. Finding out someone else did what you have been trying to do for the last couple of months.
Oh yeah, that happened to me as well. Yeah,
nice.
That can happen, and just move forward, and you have to remind yourself constantly why you're doing it.
Yeah. And you always learn a lot on the way. Yeah, so I think this is a cool way of ending it. Thanks a lot for joining us, and I had a lot of fun. Super cool conversation.
Thanks for having me. It was a pleasure.